So we're going to talk about the general principles, the diagnosis of the patient, the evaluation of the patient, and how we treat the patient with hypertension. So
Yep.
the resistance, as we said, it's very important for us to assess the amount of the flow and how much flow goes in must be determined for a given pressure in the circulation or in the network that we are examining. So we are talking about our cardiovascular network. So we calculate the resistance from the knowledge of the individual elements of the system. So we have arterial element, arteriolar element, capillary, venous segments, and all these factors are connected in a series. So they are connected together in a regular way. So arteries, arterioles, and capillaries, and also veins are connected in series. Within each segment, there are many vessels arranged in a parallel. So the resistance between each compartment of the network is in parallel, but between all the compartments together, it's in series. So you will see a picture that will illustrate everything. So it's clear, I think. Here are the arteries, and here are the arterioles, and here are the capillaries, and here are the venules, and here are the veins. So you can see that the connection between the arteries and the arterioles is in series. They are continuous, and with the capillaries is in series, and with the veins and venules is in series. But the venules together, they are arranged in parallel. So the resistance between the veins themselves, venules, capillaries, arterioles, and arteries, it's in parallel. But between each category and the other, it's in series. So this difference is very important because if you increase the resistance in the arteries this way, if they are arranged this way, if you increase the resistance in the arteries, the resistance in the arterioles will increase, and in the capillaries will increase, and in the venules will increase, and in the veins will increase as a part of the total resistance, not the individual resistance. So I'm not talking about the arteriolar resistance itself and the capillary resistance itself and the venous resistance itself. If the arteries increased in their resistance, the total resistance that consider the arteries, veins, venules, arterioles, capillaries will be increased. But if I increase one artery resistance, the total resistance of the arteries will be decreased. So when the resistance are arranged in parallel, when one of the component of this resistance is increased, the total resistance will be decreased. And when are they arranged in series, if you increase a resistance, it will increase the total resistance. So you can look at this table, coming table, make it more clear. You have to know the variation between each segment of the cardiovascular network. So what is the largest segment in the diameter? It's the
Mm.
aorta,
Aorta.
the largest one, the aorta. And where we can find the greatest wall thickness, it's again the aorta. The number, where is the largest number? It's here
Mm.
in the arterioles,
Mm.
or I think, yeah, it's in the arterioles, not the capillaries. So the total cross-sectional area, it's higher where? In the arterioles, in the capillaries. And the total amount of blood found where? In the veins. Venous system contain the highest volume of the blood in this circuit. So you have to know that vessels in series, the overall resistance of the network is simply the sum of the individual resistance, i.e., if you have three systems, R1, R2, R3, so the total amount of the resistance equal R1 plus R2 plus R3. So it's Rn plus. So if the resistance in R1 increased, the total resistance will be increased. I think it's clear. So a more illustrative diagram will follow. You can see here that there is a pressure at the start of this segment and a pressure at the end of it. And through this segment, there is a flow. So this is the first segment, this is the second, this is the third. And they are named R1, R2, R3. This is R1, this is R2, this is R3. So the total resistance equal R1 plus R2 plus R3. So as long as R2 is narrower, it have a higher resistance because the smaller the radius, the higher the resistance. And for us to know the flow, we need the delta pressure and the resistance. So we need the total resistance. We need the difference in the pressure between P1 and P2. The difference in pressure here between the start of this segment and the end of this segment. So delta pressure is calculated and the total resistance is calculated. So the flow is calculated. And the flow is dependent on the resistance and the pressure. You can see here in the first segment, the pressure is high and the flow is high. It coming to decrease as long as we are going because the resistance is increasing. So as long as the resistance is increasing, the flow is decreasing. Okay? If you want to calculate the individual flow for each department, for example, for R1, so we will we will consider the delta pressure for R1. The delta pressure 1, the flow is static, and the resistance is specific for the specific segment. The same for the second and the same for the third. We can calculate each individual difference in the pressure and the resistance for each segment, and we can calculate the total resistance. So we can know individual resistance and total resistance. And this is a very important issue in the setting of organ transplantation, because when we remove an organ, we are disturbing the total resistance. And when we are placing an organ, we are changing the total resistance. So it will affect the blood pressure. And when we are having a patient with vasoconstriction in specific organs due to administration of medications or due to a state of sympathetic stimulation, because sympathetic stimulation causes vasoconstriction in some organs and vasodilation in others because of the effect of the norepinephrine and epinephrine, because the epinephrine, as we said, causes vasodilation in skeletal muscle in the previous lecture, and norepinephrine causes vasoconstriction generally in the body. So the difference in the resistance between organs affect each organ differently and affect the systemic circulation differently. So this is what we can say about vessels arranged in series. What about vessels arranged in parallel? The overall resistance for parallel network according can be calculated according to the following formula, which is the total resistance equal the sum of the reverse resistance for each segment, and the total flow is also determined by the change in the pressure. So this is the formula. You can see that we have a system that having three segments, and each one have its own resistance. They are referred to as R1, R2, R1, R2, and R3. And here is the starting point, and this is Pi or P1, and this is P0. So this is the difference of pressure between Pi or P1 and P0 is the delta pressure that we need to calculate the total flow, and the total resistance to be calculated. We need to know what is the relationship between the segments. Is it series or parallel? If it's series, the total resistance equal R1 plus R2 plus R3. But if it's parallel, it will be this way: the reverse of R1 plus the reverse of R2 plus the reverse of R3 equal the reverse of the total resistance. So if you have an increase in if you have an increase in R3, for example, if it was if R1 were 1, 2, and R3 were 2 also, or it were 3, so it will be 1 plus half plus third, right? So it will be 1 over R total resistance equal, say it's 2, so it will be 2, 1 over 2, right? So the total resistance will be 2. So
Okay.
if we increase if we increase R3 from 2 to 3, it will be 1 plus 1 over 2 plus 1 over 3, right? So it dropped actually because third is less than half, correct? So
Yes.
the value will be less than 2. The final value will be less than 2. So resistance in parallel will, will decrease when a single resistance increases. So if R1 or R2 or R3 increase, the total resistance will be decreasing. This is why capillaries are the most narrowest segment in the vascular system, but still they have the smallest pressure. We know that pressure equal flow time resistance, right? So if the resistance increases as the radius decreases, it's reasonable that the pressure increases, right? And we said that the capillaries have the smallest diameter. So why it still have the smallest pressure and fluid exchange occur at the level of the capillary? Do you know why? So this occur because of the arrangement of capillaries in parallel circuit. So we will go to the next slide, and it's about the normal conditions in the peripheral vasculature. So we are dealing with peripheral blood flow velocity. What is the flow velocity and what is the normal flow velocity and how we estimate them, and the peripheral blood volumes and the peripheral blood pressures and the peripheral vascular resistance. These are the important measures in the cardiovascular physiology: velocities, volumes, and pressures and resistance. Where do you think is the highest flow velocity? The highest flow velocity will be in the arteries, not arterioles, and the highest blood volume will be in the veins, and the peripheral blood pressure will be at highest in the arteries, and the vascular peripheral resistance will be at highest in the arterioles.